Our next molecule is alpha minus multistriatin. The structure is, it's a 6-membered ring, just like our glucose molecule, with the O group 5-membered ring on the top of it. So this is the multistriatin. It's a sex pheromone. It is used by insects to attract female. This is your carbon number 1, 2, 3, 4, 5 and 6. So if you look at this carefully, this structure is something like a glucose, where carbon number 1 having one OH, which is forming a bond with the sixth carbon OH. So that you can imagine. But the change is, at carbon number 1 there is one ethyl group. At carbon number 2, instead of OH we have a Me group. At carbon number 3 we have OH, which is replaced by hydrogen, and at carbon number 4 we have the Me, that is methyl group, at the place of OH. 5 is CH2OH, so that is as it is. So we need to play with the carbon number 1, 2, 3, 4. So one can imagine this structure can be obtained from the glucose molecule, and let's see the retrosynthesis of this. So if I write down the structure of the multistriatin, we can imagine this is, first I can break this bond at this place. So we can have the structure CH3, CH2, CH3 with the OH group, CH2, OH and CH3. So that's a very obvious break here, which also, actually this structure we have written, this is carbon number 1 and 4. So I call this as a 1C4 structure. You can see the meaning of 1C4 and 4C1 in another video. So which we can now convert into 4C1 structure by writing the structure in this fashion. The same structure is written in this form, in the 4C1 form, where all the things and their connectivities are retained. This structure, one can imagine, is formed from, so this is the break one can think of. We can get the structure like this, but actually in before that, let's go for the retro of this, which looks like this structure. So you can think of the breaking here, this bond, breaking of this bond here, breaking of this bond will give you the structure like this, which is, we can say, it's again the hydroxy aldehyde, and which is 3-deoxy. So 3-deoxy hydroxy aldehyde. So these are the two OH groups what we have. So this structure can then be written with this is CH2 CH3. So we can think of removing this CH2 CH3 also. So we will get the structure which looks like This is what, this was 3 hydroxy ketone, and now we will get 3 deoxy hydroxy aldehyde, and this structure is actually written in this form. Anyways, so we will continue with our this structure which was written here. We'll go for the retro of this, where we are going to have the introduce this CH3 at this stage. So we will have the alpha epoxide, so we have the OH, we have the O and the CH3 and CH2COH. So this is what we get, the alpha epoxide. Alpha epoxide, one can think from the protected glucose molecule, where we have one OH, O and the double bond O here with the OH group, and this is eventually obtained from D-glucose. So let's go again. We have a multistriatin. One can think of retrosynthesis by first, so we said we have the changes at carbon number 1, 2, 3 and 4. So we can think of the first change between the opening of this bond. So we have the breaking here, opening of this bond. Then we have converted 1C4 into 4C1 structure, and this 4C1 structure we can think of breaking here between the first carbon and the oxygen. So we have a open chain structure which is a 3-deoxy. This is your third position, 3-deoxy hydroxy ketone. This can be, one can think of, which is obtained from CH2 CH3 that can be introduced at this stage. We'll see all those steps there. So we have the 3-deoxyaldehyde here, and these 3-deoxyaldehyde can be written in this ring form like this, which is obtained from the alpha epoxide, and then the ketone group here eventually mainly obtained from the D-glucose. We'll go step by step the synthesis of alpha minus multistriatin. In the synthesis, we take the D-glucose molecule. Here we are going to write down the structure, again the 4C1 form. So you know that this is the alpha D-glucose molecule. Alpha, because the OH group at first carbon atom is down, so alpha D-glucose. We will treat this with the methanol in presence of H+. So we have already learned in another video of ours that methanol in presence of acid will protect or trap the OH group here. So we will get the formation of the protection as OCH3. This will keep the ring in the ring format, structure in the ring format, and it will not open to give the structure, it will not give the open chain structure of the D-glucose. Now we are going for the protection of, this is carbon number 1, 2, 3, 4, 5 and 6. We are going for the protection of 4 and 6 carbon atom. There are so many OH groups are there now. Still we have protected only one of them. Total 5 OH groups were there, we have protected one of them. So now we are going to protect the carbon number 4 and 6, these OH groups. So that is done by treatment with benzaldehyde. We have seen that also in one of our videos, that is how to trap the molecule in the different conformations. So when you take the benzaldehyde in presence of ZnCl2, we will get the protection of the fourth and sixth carbon atom. So OCH3 here, OH, OH, and now this will have another ring, H and pH. So this is going to protect the 4 and 6 carbon atom. So this is especially protecting 1,3-diol. So one must know that benzaldehyde is generally used to protect 1,3-diol. So we have protected now the position number 4 and 6, we have protected position number 1 also, and now the two positions are left, two OH are left, that is at position number 2 and 3. So now we will protect by taking 2.5 equivalent of TSCl in presence of pyridine. We will protect the carbon number 3. So this is your carbon number 3. So carbon number 3 will give you the structure like this. In fact, both the, not only carbon number 3, both carbon number 2 and 3 will get protected. Both will form OTS, and this is, now we are going to form the alpha epoxide by using the catalyst like CH3ONA in presence of chloroform. What happens in this, it will generate the OCH3 part, and this OCH3 part will attack, like suppose if you have the tosyl group written like this for this carbon atom at C2, so it will attack on the sulfur and this bond will go here. So we will get eventually the O minus here. So we get O minus, and now it will attack on the OTS. I am not writing this remaining part, look at this. So if this O minus is formed, this will attack here and OTS will go. So we will get a structure that looks like OCH3, and here you get the alpha epoxide formation. The rest of the things are as it is. Let's go back again. What has happened? Here we have a D-glucose. We have protected the first carbon atom, that is anomeric OH with the OCH3 by treatment with the methanol and H+. Then this is treated with benzaldehyde, which will protect the carbon number 4 and 6, 1,3-diol. So we have protected that also. We are left with the 2 OH free group, that is at position number 2 and 3. And now we will treat with the tosyl chloride. Tosyl chloride will protect both the OH group here. Then we are going to treat this with the sodium methoxide in presence of chloroform. Here what happens, this will generate the OCH3 minus, this OCH3 minus, this is the tosyl group at C2 what we have written. So this will attack on the sulfur and this bond will go as O minus. So here at this position O minus will be formed like this, and this O minus, this is the new generated O minus, will attack on this carbon atom and OTS will go. This is what is shown here. So we get the formation of alpha epoxide. This is then treated with the Me2Culi in presence of ether. So we will get a reaction where now the methyl Me minus, this group will attack on the second carbon. It will attack on the second carbon, and the O, that epoxide ring will open up. So we will get the formation of OCH3, and now here you get a first introduction of that CH3 group at second position. We will get it here, the OH, and the remaining things are as it is. Fine. Now we have a Barton protocol by which we are going to convert this third carbon, the third OH into H. So for that we will treat this with the NaH in presence of CS2 MEI, and secondly we will treat with the NBU3SNH in AIBN and benzene. So here Barton, as I said, we said Barton protocol where we are going to replace this OH by H. So rest all things will be exactly same, and we will get the H and H here. Rest all the things are same. Okay, fine. Now we will have the 2-deoxy sugar we have generated. This is treated with tosyl OH, MuOH. So where we will break the protection on carbon number 1, 4 and 6. So we will get a the ring where this is OCH3 as it is, this CH3 is there, now this is H and this is OH and this is another OH. So now you can see we have converted carbon number 2 and 3 in the required form. We are left with carbon number 4 and 1. So we will now treat this with the trityl chloride. Trityl chloride we already have seen in some other synthesis, which has the triphenyl methyl chloride. It will protect only the primary OH, this at carbon number 6, at C6 and C4 will remain as it is. So we will get the structure which looks like, so keep writing the other things as it is, OH, and this is the primary OH group being protected with the TR group, trityl group. Now this carbon number 4 is free. We will treat this with the Collins reagent, which is CrO3 in pyridine. So that will undergo the oxidation. So we will have the OCH3, CH3, CH2, double bond O and the OTR. So this TR group will be here. So now we have the C double bond O, which will carry out the Wittig reaction with the reagent triphenyl phosphine double bond CH2. So we can imagine the CH2 will come at this place. So we will get, in all the cases we are writing 4C1 structure. So this is CH2 at this place, OTR as it is. We will now use the Wilkinson's catalyst to reduce this. Wilkinson's catalyst is for the reduction, which is in the homogeneous medium. So this will become CH3, OCH3, CH3. Don't forget this CH3 at C2 position. We have already introduced that. And this will become CH3. Okay, and then this is treated with the propane dithiol, that is SCH2, CH2, CH2, SH. So this is propane dithiol. What it is going to do is, first it will react with this, will form a double bond, and okay, let's first write down what we will get, a formation of double bond like this. Sorry, this will form a plus charge. This is OTR, CH3, and we don't have a bond here. This OCH3 is gone, and now this lone pair will attack on this carbon atom and double bond will go, and eventually what one can think that the cyclization will take place at that. So let's write down first the structure. S and CH2, CH2, CH2 and SH, and of course the rest of the things are OTR and CH3 as it is. So now what is going to happen is, this lone pair, another lone pair will attack in presence of, we have the BF3 iterate. So what is going to happen is that BF3 will come here with this, and this will attack on this carbon again, and this will open up. Fine. So eventually, let's see what we get. This will become OH, BF3, and then OH, and we have the OTR there as it is. This CH3 and SS and the H. There was one H here, of course. So we will eventually, what we are going to get from this reaction, Wilkinson's, you must have understood that this becomes CH3. Now we are going to treat this with the propyl and the dithiol. So propane dithiol we will treat this with in presence of BF3 trait. What is going to happen is this ring is going to break, and this will become OH. OCH3 will go. We have seen how it will go, that this first attacks here and then again go back. So it is like this, it is coming here and going back. We have a double bond formation earlier, and then again it opens up. OCH3 is going, so this SH which was there will attack here, and then this SH will attack on the same carbon atom. This will open up and eventually it becomes the OH group. Fine, we will treat this with the base, a very strong base, that is T-butyl tertiary butyl lithium. It is going to abstract this proton which was there. This proton it will abstract, it will form a negative charge. So we will get something like this, that is S, and all these things are there, and this H which is there. So all these things are there. Of course, this H which is was there will form a negative charge. This negatively charged will treat this with the CH3 CH2Br. It will attack on this. So what we are going to do now is we are going to replace this H with the CH3 CH2Br. So for that we will use the N-butyl lithium, which will make a carbon ion, and then it will attack on the CH3 CH2Br. So this part will become CH3 CH2 CH3. So we have introduced the ethyl group at first carbon atom. So step by step we are going for this is CH3, and this S is still there, and CH2 CH3. So we have formed a CH2 CH3 at this place. This is then treated with HgCl2 in aqueous CH3Cn, and we are going to reflux this. So what happens is we are going to break this dithiol group. We are going to break this dithiol. So we will get the structure, and at the same time we are going to replace the OCH3. So we will get OH, deprotection of this also as OH, CH3, CH2 CH3, and COCH2 CH3. Then there is one CH3. Let's count the number of carbon atom. This is one, what we have, the OH, and then the carbon number 4 with the CH3, carbon number 3 with this, carbon number 2 with this. Okay, there was CH3 here. Sorry. Okay, so we will get a ketone formation like this, and now we are going to have this where the lone pair of this will attack on the CO group and the OH opens up. So we will get a ring formation where the OH will be formed here and CH2 CH3 at this place, OH, this CH3, and there are 2 hydrogens, what we have seen at C3. Almost done. We have the structure. We are reached to the almost end of the end part of it, where we need to write down this structure, which was 4C1 structure, will convert into a 1C4 structure. 1C4 structure. So we are going to take this 1 up and 4 down. The structure will look like where now the carbon number 1 is here. So we have now the OH group on the pointing upward, ethyl group here, the methyl group is now pointing upward, which was here. Axial will become equatorial. Carbon number 3 does not have anything, no substituents, 2 hydrogen atom. Carbon number 4 is here, which will have the CH3 equatorial. Carbon number 5 will have CH2 OH. So you can see, look at the main structure here, is we just are now left with the ring formation of carbon number 1 and 6. This was your number 1 and this was your 6. So we will now have the ring formation by loss of water, and that will going to give you the alpha minus multistriatin as your final structure. So this is a very interesting and meticulously planned synthesis, where we are going to have the synthesis. Let's do the in short what we have done. This is the multistriatin main product what we want to synthesize, which is a hormone, insect hormone. The retrosynthesis of that can be envisaged from the D-glucose molecule. This D-glucose molecule, when we start the synthesis, first we protect the OCH3. As we said, there are 4 positions we need to uh, make the changes. So thus first protected at carbon number 1, then protected at carbon number 4 and 6, and now tosyl chloride will make this both the OTS by treatment with the base like CH3ONA and CH3Cl. It will form the alpha epoxide. The mechanism what we have seen is OCH3 attacks the tosyl group first, forms the O minus like this. This O minus will have the displacement reaction at C3, and we will get a alpha epoxide. We will treat with the Me2Cu Li in presence of ether, where the minus Me minus is generated. Methyl with the negative charge is generated, which is going to attract on this, and the epoxide ring will open up. Then we have a Barton protocol, which is famous for converting OH into H. So we will have the 3-deoxy sugar. At the third place we want the CHH only. So 3-deoxy sugar is formed. This 3-deoxy sugar is then treated with the tosyl, and now here MeOH, and then finally with the trityl chloride, where we protect this. So eventually what one can think of, the OH which is at carbon number 4 is free, which is oxidized with the Collins reagent and then Wittig reagent, and then the Wilkinsons will make this CH3 what we want at carbon number 4. This is then treated with the protected with the propane dithiol, where the ring opening will take place like this, and tertiary lithium will remove this hydrogen, and treatment with the CH3 CH2Br will add the ethyl group at that required position, and then the cyclization will take place, and then here we have a final cyclization to give the final structure of alpha minus multistriatin.